So as an exercise, let A be the 3 by 3 matrix with rows 3, 4, 1, 2, -7, -1, 8, 1, 5, and let B be the 3 by 3 matrix with rows 1, 11, 2, 2, -7, -1, 8, 1, 5. Find the elementary matrices E and E prime that satisfy the equations A is equal to E times B and B is equal to E prime times A. And then show that E prime is the inverse of E. So next we'll prove a theorem. Every elementary matrix is invertible and its inverse is also an elementary matrix. So proof. Let E be an elementary matrix and let E prime be the elementary matrix obtained by performing the inverse of the operation that produced the elementary matrix E from the identity and this inverse is performed on the identity. Then the product E prime times E is the matrix that results from applying the inverse of the operation that produced the matrix E from the matrix I, and this inverse operation is performed on the elementary matrix E, that is, E prime exactly reverses the process that resulted in E, and so E prime times E leaves the identity matrix unchanged. Similarly, the product E times E prime is the matrix that results from applying the inverse of the operation that produced E prime from the identity, and this inverse operation is performed on the elementary matrix E prime, that is, E times E prime is the identity, and hence E prime is the inverse of the elementary matrix E, and therefore the elementary matrix E is invertible. And its inverse is also an elementary matrix. So as a corollary, let A be an invertible matrix if the matrix A is row equivalent to a matrix B, then that matrix B is also invertible. So proof: since the matrix A is row equivalent to the matrix B, there exists a finite sequence of elementary row operations that produce the finite sequence produces the matrix B from the matrix A. In other words, there exist elementary matrices E sub 1 through E sub k for some finite number k, such that B is equal to the product E sub k and so on through E sub 1 times A. Now, since each elementary matrix is invertible, and the matrix A is invertible, the product of the elementary matrices and the matrix A, which is the matrix B, is invertible. Okay, so new definition. Let A be an M by N matrix with row entries. Then the matrix A is in row reduced echelon form. And I will abbreviate this RREF if it satisfies the following properties. First, if a row does not consist entirely of zeros, then the first number in that row is a number 1, and we call this a leading 1. Second, if there are rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix third, and any two successive rows that do not consist entirely of zeros the leading 1 in the lower row occurs farther to the right than the leading 1 in the higher row. And fourth, each column that contains a leading 1 has zeros elsewhere in that column. And a matrix must satisfy all 4 of these properties in order to be in row reduced echelon form. So let's look at an example. Let A be the 3 by 3 matrix with rows 1, 2, 3, 4, 5, 6, 7, 8, 9. Find the matrix in reduced row echelon form, that is row equivalent to the matrix A. So we begin with the matrix A. And we notice that in the first row, we have a leading 1. So in that column, we need all other entries to be 0. And so we need to remove or cancel the 4 and the 7. So first, we will multiply by -4 times row 1 and add this to row 2. -4 plus 4 is 0. -8 plus 5 is -3. -12 plus 6 is -6. So now we need to cancel the 7. And so we will multiply row 1 by -7 and add this to row 3. So -7 plus 7 is 0. -14 plus 8 is -6. -21 plus 9 is -12. Now in the second row, we need for the first number to be a leading 1. And so we will multiply row 2 by -1/3. And so in row 2 we have 0, 1, 2. And so now we have a leading 1 in row 2. And so in that column we need for the other entries to be 0. And so first we need to cancel the 2 in the first row. And so we will multiply row 2 by -1 and add that to row 1. Correction, we'll multiply row 2 by -2 and add that to row 1. -2 plus 2 is 0. -4 plus 3 is -1. And so now we need to clear the -6 in row 3. And so we will multiply row 2 by 6 and add that to row 3. Six plus 6 is 0. 12 plus 12 is 0. And now we have a matrix that is in row reduced echelon form that is row equivalent to the matrix A.